Throughout the vast expanse of the cosmos, stars are born, they live, and they die. Some fade away quietly, while others meet a spectacular end, a supernova. These cosmic explosions are among the most powerful and luminous events in the universe, capable of outshining entire galaxies for a brief, shining moment. In this exploration of the cosmos, we'll journey to the heart of these celestial fireworks, unraveling the mysteries of supernovae. We'll delve into the science behind these explosive events, discover the different types of supernovae, and explore their profound impact on the universe and even our own existence. So fasten your seatbelts and prepare for a cosmic adventure as we explore the awe-inspiring power of supernovae, the explosive death of stars. Imagine a star, a colossal sphere of hot, glowing gas held together by its own gravity, a celestial body that has fascinated humanity for millennia. These stars are not just static objects, they are dynamic, ever-changing entities. Within these cosmic furnaces, nuclear fusion reigns supreme. For millions, even billions of years, stars exist in a delicate balance, fusing hydrogen into helium in their cores, releasing the energy that makes them shine. This process is what gives stars their brilliance and longevity. But this balancing act can't last forever. Over time, the fuel that powers these nuclear reactions begins to run out. You see, for massive stars much larger than our own sun, their fate is sealed from the moment they're born. These stars are destined for a dramatic end. These stellar giants live fast and die young, their immense gravity driving them to consume their nuclear fuel at an extraordinary rate. They burn through their hydrogen much faster than smaller stars. As hydrogen in the core depletes, the star begins to fuse heavier elements like helium and carbon in a desperate attempt to sustain itself. This process continues with elements like oxygen, neon, and silicon. Each stage of fusion produces less energy than the last, pushing the star closer to its inevitable demise. The core becomes increasingly unstable. Eventually the core, no longer able to withstand the crushing force of gravity, collapses in on itself in a fraction of a second. This collapse is incredibly rapid and violent. This implosion sends shockwaves outward, ripping through the star's layers, igniting a runaway nuclear reaction that unleashes an unimaginable amount of energy. The star's outer layers are blasted into space, and just like that, in a cosmic flash, a supernova is born. This explosion is one of the most powerful events in the universe. The star, once a beacon of light, becomes a brilliant beacon of its own destruction, briefly outshining its stellar neighbors. The remnants of this explosion can form new stars, planets, and even life, continuing the cosmic cycle. Now, not all supernovae are created equal. These cosmic fireworks come in various forms, each with its own unique characteristics and underlying mechanisms. In fact, astronomers have categorized these stellar explosions into different types, each with its own unique story to tell. By studying these events, scientists can unravel the mysteries of the universe and understand the life cycles of stars. One type, known as a type Ia supernova, involves a stellar remnant called a white dwarf. These remnants are the cores of stars that have exhausted their nuclear fuel and shed their outer layers. White dwarfs are the dense, Earth-sized cores of dead stars that have exhausted their nuclear fuel. Despite their small size, they are incredibly dense, packing a mass similar to that of the Sun into a volume comparable to Earth. Now, imagine a white dwarf in a binary system, locked in a gravitational dance with a companion star. This close relationship can lead to dramatic consequences. As the white dwarf orbits its companion, it begins to pull material, hydrogen, and helium from its companion's outer layers. This process is known as accretion. This stolen material accumulates on the surface of the white dwarf, increasing its mass. Over time, this accumulation can lead to a critical situation. But there's a limit, a critical mass, known as the Chandrasekhar limit. This limit is approximately 1.4 times the mass of our Sun. If the white dwarf accretes enough material to exceed this limit, a runaway nuclear reaction ignites, consuming the white dwarf in a thermonuclear explosion. This results in a spectacular Type Ia supernova. These Type Ia supernovae are incredibly luminous and remarkably consistent in their brightness, making them invaluable tools for astronomers to measure cosmic distances. They serve as cosmic mile markers, helping us map the vast expanse of the universe. But what about those massive stars that collapse under their own weight? These giants have a different fate awaiting them. These stars meet their end in what we call a Type II supernova. Unlike Type Ia supernovae, these explosions are the result of the core collapse of a massive star. As the core collapses, it forms an incredibly dense object, either a neutron star or a black hole, and the outer layers of the star are ejected into space at incredible speeds. This violent process not only marks the death of a star but also seeds the cosmos with heavy elements, contributing to the ongoing cycle of stellar birth and death. Chapter 3. Stellar Remnants, Echoes of a Star's Demise. In the aftermath of a supernova, the universe is forever changed. These colossal explosions mark the end of a star's life cycle, but they also herald the birth of new cosmic phenomena. The immense energy released by these explosions creates some of the most extreme and fascinating objects in the cosmos. From the remnants of these stellar giants, we witness the formation of neutron stars and black holes. Let's start with neutron stars. These are the incredibly dense cores left behind after a supernova has blown away the outer layers of a star. These bizarre objects are the remnants of massive stars that have exploded as Type II supernovae. The process compresses the core to an unimaginable density. Imagine a sphere no larger than a city, yet containing more mass than our sun. This is the reality of a neutron star, where matter is packed so tightly that a sugar cube-sized amount would weigh 1 billion tons on Earth. The gravitational pull of a neutron star is so strong that atoms themselves are crushed, leaving behind a sea of neutrons. This immense gravity also affects time and space around the star. But neutron stars aren't just incredibly dense, they also spin rapidly, some rotating hundreds of times per second. This rapid rotation generates powerful magnetic fields. As they spin, these cosmic lighthouses emit beams of radiation that sweep across the cosmos, creating what we observe as pulsars. These beams are so regular that they can be used as cosmic clocks. Now, if the core of the collapsed star is massive enough, even the immense pressure of neutrons cannot withstand the relentless pull of gravity. This leads to an even more dramatic transformation. In these cases, the core collapses further, forming an object of infinite density and zero volume, a black hole. This is where the laws of physics as we know them break down. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape their grasp. They are the ultimate cosmic traps. They are cosmic enigmas, warping the fabric of space-time and challenging our understanding of the universe. These mysterious objects continue to intrigue and baffle scientists, pushing the boundaries of our knowledge. Chapter 4. Cosmic Detectives, Unmasking Supernovae. For centuries, astronomers have gazed up at the night sky, observing these celestial fireworks from afar. But how do we detect and study these distant explosions? One way is through telescopes, both on the ground and in space. When a supernova occurs, it releases an enormous amount of light, making it visible across vast cosmic distances. Astronomers use powerful telescopes to capture this light, allowing them to study the supernova's spectrum and learn about its composition and properties. Another tool in our cosmic arsenal is supernova surveys. These surveys scan the sky for signs of new supernovae, looking for sudden changes in brightness that could indicate a stellar explosion. By monitoring millions of galaxies, astronomers can detect dozens of supernovae every night. But light isn't the only messenger from these cosmic cataclysms. Supernovae also release tiny subatomic particles called neutrinos. These ghostly particles can travel through space unimpeded, carrying information about the heart of the explosion. Neutrino detectors, buried deep underground, can detect these particles, providing us with a unique glimpse into the supernova process. Chapter 5. Supernovae and the Cosmic Cradle of Life. Supernovae are not just destructive events, they are also essential for the creation of the elements that make up our universe, including the building blocks of life itself. Think about it. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of these elements were forged in the fiery hearts of stars. And when these stars explode as supernovae, they scatter these elements into the cosmos, enriching the interstellar medium with the raw materials for new stars, planets, and even life. In fact, our own solar system owes its existence to a supernova that occurred billions of years ago. The shockwave from this explosion is thought to have triggered the collapse of a giant cloud of gas and dust, giving birth to our sun and the planets that orbit it. So, as you look up at the night sky, remember that you are connected to the cosmos in a profound way. The atoms in your body were once part of stars that lived and died long ago, their ashes scattered across the universe, only to be gathered up again to form new worlds. Outro, Stardust to Stardust. Supernovae are catastrophic yet creative. They end one star's life but spark new cosmic beginnings. They create black holes, neutron stars, and nebulae. They spread heavy elements across the universe, forming planets and life. They help us understand cosmic expansion and the fate of the universe. These cosmic explosions are a testament to the awe-inspiring power of the universe and the intricate cycles of stellar life and death. The next time you look at the night sky, remember, you are made of stardust, created by the fiery death of ancient stars. What do you think? Could another nearby star go supernova in our lifetime? Let us know in the comments.